You hear it everywhere, right? AI is completely changing software development. Our coding assistants can finish our sentences, suggest whole blocks of code, even write entire scripts from scratch. But let's be real for a second. Beyond all the hype, how do these super powerful tools actually handle the messy, complicated, and let's face it, often frustrating reality of real-world coding? Can an AI really fix your code?
See, the problem kind of boils down to how we've been testing these AIs. Most of the tests out there are like a 100-meter dash. They're short, self-contained problems. But actual software engineering, that's an Ironman triathlon. We're talking about massive, sprawling systems where fixing one tiny little bug means you have to understand the entire landscape. And that, my friends, is a whole different ballgame.
So to really put these AIs to the test, some brilliant researchers from Princeton and the University of Chicago decided to build a new kind of test. They built a real-world gauntlet, something designed to mirror the exact challenges human developers face every single day. And they called it SWE-bench.
So what exactly is SWE-bench? Well, imagine a collection of over 2,000 actual software engineering problems, pulled directly from 12 of the most popular Python projects on GitHub. We're talking about giants like Django, scikit-learn, and matplotlib. And the task? Oh, it sounds simple, but it's incredibly tough. The AI gets the entire codebase and a real bug report from a user. Its job is to generate the exact code patch to fix the problem. No hand-holding, no shortcuts.
Now, what makes this benchmark so powerful is just how rigorous they were in building it. They didn't just grab any random bug report. No way. They started with a mountain of data, nearly 90,000 pull requests. From there, they started filtering. They only kept the ones that were actually merged, solved a specific issue, and, this is key, added new tests. And for the final step, they only included tasks where they could prove the fix worked by running those tests and watching them go from a fail to a pass. This makes sure every single problem is a high-quality, verifiable, real-deal challenge.
And the scale of this challenge is just mind-boggling. On average, the AI had to navigate a codebase with over 3,000 files and almost 500,000 lines of code. It's a huge sea of complexity. And yet, the average fix made by a human, it only involved changing about 33 lines of code across like 1 or 2 files. So the task isn't about writing tons of new code. It's about finding the exact right needle in a haystack and making a tiny, surgical change.
Okay, so the gauntlet is ready. Now it's time to bring in the champions. The researchers took the most advanced language models out there and threw them into the ring with SWE-bench.
And the contenders are the heavyweights, the ones you've all heard of. We've got OpenAI's GPT-4, Anthropic's Claude 2, and even a specially fine-tuned open-source model called SWE-Llama, which was trained specifically for these kinds of tasks. We're talking the best of the best. And the stakes here are incredibly high. As the researchers themselves put it, this isn't just about generating code, it's about deep understanding, about coordinating changes across functions, classes, and even different files all at the same time. This is as much a test of reasoning as it is a test of coding. All right, the stage is set. The most powerful AIs on the planet versus the most realistic coding challenges ever created. Before I show you the results, just take a second. How do you think they did?
Let's find out. The results were shocking, to say the least. The top-performing model, Claude 2, only solved 4.8% of the problems, and GPT-4, a tiny 1.7%. But here's the real kicker. This was in the Oracle setting. That means for every single problem, the AI was literally told which files it needed to edit. Even with a massive cheat sheet pointing to the exact location of the problem, the success rate was just incredibly low.
Let's just let that sink in for a second. 1.7%. That's GPT-4's score on these real-world challenges, even when it knew exactly where to look. This just goes to show you how massive the gap is between those simple coding puzzles and the real thing.
And what happens when you take those training wheels off? When you remove that hint and the AI has to find the right files all on its own, just like a human developer? Well, performance completely cratered. Claude 2's score was cut by more than half, dropping from 4.8% all the way down to just under 2%. This proves a huge part of the challenge isn't just fixing the bug, it's finding the dang thing in the first place.
Now, these scores aren't just a bad report card. They're actually a diagnostic tool. They tell us exactly where today's AI models are falling short, and they reveal the key challenges these systems face when they step into the real world. So first up is what we can call the context problem. You would think that giving an AI more information, more code, would help it, right? Nope. Turns out the models get lost in the noise. Their performance actually got worse when they were shown a bunch of unrelated code. In one experiment, researchers carefully cut out all the irrelevant stuff and only showed the AI the exact lines that needed changing. And guess what? Performance for models like GPT-4 more than doubled. It turns out more isn't always better.
Next, there's a huge difference in the type of solutions they come up with. AI fixes tend to be very simple, almost greedy. They make the smallest possible change to pass the test, usually just editing one file. Human developers, though, we think about the bigger picture. We often make larger, more structural improvements that don't just fix the immediate bug, but also make the code better for everyone else down the line.
And the list just keeps going. The AI struggled with really basic stuff, like generating a correctly formatted patch file. They'd often write simple code from scratch instead of just using powerful libraries that were already right there in the codebase. They'd ignore established coding styles and best practices. Basically, they acted like someone who knows the Python language, but not like a software engineer who knows how to work on a team and contribute to a large, ongoing project.
So, after seeing all this, what does it really mean for the future of AI in coding? Are these tools just stuck being glorified autocompletes forever?
Probably the best way to think about it right now is this. An AI coding assistant is like a brilliant, super-fast intern. It is fantastic at well-defined, isolated tasks. You can tell it to write a specific function, explain a snippet of code, or help you brainstorm some ideas. But you wouldn't ask an intern to go independently diagnose a complex bug in a mission-critical system and deploy the fix all by themselves. That takes experience, context, and a holistic understanding that, frankly, these models just don't have, at least not yet.
And that's really the key takeaway here. This research isn't a story about AI failing. It's a roadmap. By creating a benchmark that truly reflects the messiness of reality, SWE-bench gives us a clear path forward. It shows us the exact skills the next generation of models need to develop to become more practical, more intelligent, and truly autonomous partners in software development.
So I'll leave you with this question to chew on. We often think the ultimate test for an AI is creation, making something amazing from a blank page. But maybe, just maybe, the real grand challenge, the much harder problem, isn't creation at all, but maintenance. The ability to step into a complex, messy, very human system and make it just a little bit better. Thanks for tuning in.